Greetings everyone, we are Team Tensor Titan 404 working to bring intelligence and efficiency to modern power distribution through smart grid innovation. We have taken up SIH problem 25064 which focuses on improving how renewable energy is integrated into distribution feeders while maintaining stable power quality. As more rooftop solar panels are added, feeders face uneven load, phase imbalance, and voltage fluctuations that are difficult to manage manually. This leads to instability and energy loss across the network. Our solution is an automated, secure, and adaptive system that balances load in real time and helps renewable energy operate smoothly within the existing grid.
So in a three-phase power system, ideally the load on all three phases should be balanced, meaning each phase carries equal currents and shares the power equally. But in reality, this rarely happens. When one phase carries more load than the others, it leads to what we call a three-phase imbalance. These imbalance causes multiple issues, including overheating of transformers, voltage fluctuations, increased system losses, and in severe cases, even equipment damage. Currently, detection of imbalance is mostly manual, based on periodic meter readings or field inspections. This means there is no real-time insight into which phase is overloaded or underloaded until the problems becomes visible. Our data-driven analysis shows that these imbalances can lead around 2 to 3% additional energy losses across feeders, delayed fault identification and inefficient power distributions, especially in networks with high number of single-phase rooftop solar panels. So this is what motivated us to design an automated system, one that continuously monitors phase currents, detects imbalances in real time, and intelligently redistributes the load connections to maintain stability and improve the power quality. In short, we are moving from manual observation to intelligent automation to make our distribution networks smarter, more reliable, and more efficient.
As we have just seen, phase imbalance creates real challenges for Kerala's power network, especially with the growing number of homes injecting solar power into a single phase. Our hardware brings the intelligence right to where the imbalance begins, that is, the household connection. Each home is equipped with a smart node module built using an Arduino or an ESP32 microcontroller, depending on the setup. We use Arduino for simple RS485 connections. It is reliable and cost effective for the dense neighborhoods, and ESP32 where we need wireless or LoRa communication across longer distances. These nodes constantly measure voltage, current, and phase using CT clamps and PSM sensors, reporting the data to Raspberry Pi installed at the transformer module. This Pi acts as a local controller, analyzing the phase loads and sending commands back to each node to switch phases using a three-phase relay module. That automatic phase balancing ensures uniform power flow, reduces transformer stress, and keeps the system efficient without manual intervention. Even if communication to the control center is lost, the Pi operates autonomously, maintaining local stability. And because grid security is critical, every command between the Pi and the nodes is encrypted, preventing false switching or the tampering. If any unusual behavior is detected, the system instantly blocks the command, protecting both the hardware and the grid. So, a hardware doesn't just sense and report, it thinks, reacts, and protects in the real time.
Let's take a moment to step back and see how all the data we collect usually moves. How information from every corner of Kerala's grid reaches a central control center and becomes the real-time intelligence. At the heart of this process is the Pi installed at each transformer. It gathers the readings from every homes, filters out the noise, and sends only what matters, a clean, meaningful data that reflects the true health of the grid. In cities and towns where network coverage is very strong, we use cellular IoT for this purpose. This allows each Pi to communicate quickly and reliably using the infrastructure that already exists. It is fast, low cost, and needs no extra wiring, an efficient choice for high density areas. But Kerala is more than cities. In our hilly and rural regions where connectivity weakens, the system adapts. Here, multiple Pis connect using LoRa mesh networks. They share data among themselves, and the one with the strongest signal, which is the gateway Pi, sends all the collected information using cellular IoT to the control center. And even in the most rarest remote spots, We use wired Ethernet links to ensure that no transformer is left isolated. Once the data reaches the control center, the real intelligence begins. A data pipeline powered by Apache Kafka handles thousands of incoming streams every second, ensuring that no message is lost. Timescale DB and PostgreSQL organize and store everything from real time readings to years of history. Then comes our analytics layer. Apache Storm reacts instantly to detect overloads and phase imbalance, while Apache Druid studies long term patterns to help the board plan upgrades and improve efficiency. All this information comes alive on our React and Grafana dashboard, where engineers can monitor every transformation in real time and see where the load is high, which phase is active, and when action is needed. The beauty of this architecture is that it's modular, scalable, and future ready. It grows with demand and adapts to conditions and keeps the grid efficient, secure, and always connected. Together, this communication and processing chain forms the digital backbone of Kerala's power network, which is fast, intelligent, and built for the energy systems of tomorrow.
I'll be walking you through the results and engineering backbone of our system. Our setup includes both home nodes and Raspberry Pi Edge nodes. Each home node uses an Arduino or ESP32 pad with PZEM004T multifunction energy meter and a 3-phase relay. For larger clusters, we use Raspberry Pi nodes, each equipped with an EM10 power monitoring meter and 4G connectivity module, ensuring reliable data transmission. All nodes are connected via Cat6 twisted pair cables, keeping wiring costs low while maintaining strong signal integrity. Now, in terms of efficiency, our system performs local computation on each node. That means all critical parameters are processed right at the source, minimizing delays, reducing external dependencies, and ensuring real-time response. For scalability, each Raspberry Pi can manage multiple home nodes, and multiple Raspberry Pi clusters can be deployed across Kerala, all linked to our central control server. This setup supports real-time graphs, insights, alerts, notification, and email summaries and emergency reports, providing a seamless and dynamic monitoring experience. Our architecture is modular, scalable, and efficient. Each layer operates independently, making it easy to expand or modify without disrupting the rest of the system. It's designed to handle thousands of processing interfaces statewide while maintaining minimal bandwidth and power consumption. So from the security standpoint, our communication system is protected end-to-end with TLS encryption, AES-256 storage security, and JWT-based authentication. This ensures data integrity, prevents unauthorized access, and safeguards against spoofing or interception, keeping our network trustworthy and resilient. In short, this is the digital backbone of our project, a smart, adaptive, and secure energy management network connecting every transformer and home node to the central control center, powering Kerala's next generation of intelligent energy management, safe, secure, and efficient.
So beyond the engineering performance, we wanted our solution to create real-world impact. The sustainable development goals which our project follows are SDG 7, SDG 9, SDG 11, which are affordable and clean energy, industry innovation and infrastructure, sustainable cities and communities. The novelty of our system lies dramatically balancing three-phase solar injection at distribution level using hybrid IoT architecture, which involves node level control using Arduino and relay, which enables real-time phasing and edge intelligence using Raspberry Pi analysis using a local grid load makes rapid phase balancing decision, and centralized coordination which involves with web and backend. Unlike the primitive solar panels, which involves grid adaptive self-correctness and energy efficient maintaining balance without manual intervention. The technical impact are reduces transformer heating, neutral current, and distribution losses. Economic impact are extends equipment lifespan, lower maintenance, and minimizing power wastage. Environmental impact encourages renewable energy. The final summary of the project is it's a smart grid phase balancing for distributed solar panels, transforming passive solar network into active intelligence and sustainable energy ecosystem. We envision a future where rooftop solar panels, which especially in Kerala, contributes optimally to balance, resilience, and smart grid approach for driving us into a sustainable energy secure world.